The Moon is no longer just a lifeless rock drifting through space. China's Chang'e 6 probe has returned with samples from the far side of the Moon, revealing materials and structures that defy established lunar models. Beneath its surface lie substances that challenge our understanding of lunar geology. While NASA has focused on Mars and deep space exploration, China has quietly developed the most methodical lunar program since Apollo. The Chang'e missions, named after the Chinese moon goddess, follow a strategic progression, each mission building on the last. Chang'e 1 and 2 mapped the Moon's surface. Chang'e 3 landed on the near side in 2013, the first lunar landing since 1976. In 2019, Chang'e 4 achieved a world first by landing on the far side, a region hidden from Earth and difficult to explore due to blocked communications. China overcame this by placing a relay satellite beyond the Moon, enabling Yutu-2 to explore this uncharted terrain. Yutu-2 landed in the von Karman crater within the massive South Pole Aitken Basin. Expected to last only 3 months, it has been active for over 5 years, sending back data that has transformed our understanding of the Moon. Chang'e 5, in 2020, returned with samples from a young volcanic region on the near side. In 2024, Chang'e 6 brought back the first ever samples from the far side. These efforts aren't just symbolic, they're laying the groundwork for a permanent lunar presence, including a moon base projected for completion by 2035. One strange find came in 2019 when Yutu-2 found a shiny, gel-like substance with a greenish tint. Spectrometer readings suggested it was impact melt breccia, glass formed under extreme heat from meteorite impacts. But its properties suggest a more recent or complex formation, unexpected on the geologically quiet far side. Next, Yutu-2 discovered translucent glass spheres up to an inch in diameter, much larger than any previously recorded. Their perfect shape and unusual clarity defy current geological models. Even more curious is their patterned distribution, hinting at unknown subsurface processes. The South Pole Aitken Basin itself is an enormous crater, likely created by a colossal impact over 4 billion years ago. This impact may have exposed the Moon's mantle. Instruments aboard Chang'e 4 detected high levels of minerals like low-calcium pyroxene and olivine, hallmarks of deep lunar interior material. Chang'e 6 returned with actual samples from this region. Lab tests confirmed they originated from deep within the Moon. Their composition doesn't match predictions, suggesting our models of the Moon's formation may be incomplete or flawed. Ground-penetrating radar revealed layered volcanic basalt beneath von Karman crater, indicating multiple lava flows. This suggests prolonged volcanic activity, surprising since the far side lacks the heat-generating radioactive elements believed necessary for such activity. Some theories propose that the South Pole Aitken impact created fractures reaching the core, or that hidden heat sources remain undetected. In 2022, scientists discovered a new mineral, Chang'e Y, in Chang'e 5 samples. This phosphate mineral, previously unknown on Earth or the Moon, contains helium-3, a rare isotope nearly absent on Earth. Helium-3 is a potential fuel for clean nuclear fusion, and its abundance on the Moon could revolutionize energy production. Chang'e 5 provided the first direct measurements of helium-3 in lunar soil. Though exact figures remain undisclosed, this confirms the Moon's potential as a future energy source. In summary, China's Chang'e program has not only accomplished unprecedented technical feats but also reshaped our understanding of the Moon. From strange materials and glass spheres to deep mantle samples and new minerals, these missions reveal the Moon as a complex, dynamic world. As China advances toward a permanent lunar base, these discoveries could usher in a new era of science, and possibly solve Earth's. The implications of China's lunar discoveries are profound. Scientists estimate the Moon may hold over 1 million tons of helium-3 embedded in its regolith. If harnessed and returned to Earth, this isotope could theoretically power civilization for centuries. Chinese researchers calculate that just 3 space shuttle-sized shipments of helium-3 could meet the world's energy needs for an entire year, if fusion energy becomes viable. However, extracting helium-3 is a massive undertaking. It would require mining and processing about 150 tons of lunar soil to extract a single gram. This means permanent infrastructure, mining operations, processing facilities, and human presence on the Moon. It's clear why China is advancing its lunar program so aggressively. Whoever controls helium-3 could control the future of energy. With potential values reaching tens of thousands of dollars per gram, the economic stakes are staggering. Water on the Moon may be an even bigger surprise. For decades, scientists believed the Moon was dry. That changed with Chang'e 5, which detected water in a sunlit region, up to 120 parts per million, ppm, in soil, and 180 ppm in a rock. But more remarkably, tiny glass beads formed by lunar impacts were found to contain up to 2000 ppm of water locked within their structures. This water is chemically bound and spread across the surface, unlike polar ice deposits. This means water may be accessible across the Moon, not just in polar craters. That's a game changer. Water supports life, can be split into hydrogen and oxygen for fuel and air, and serves as radiation shielding. Future lunar bases could be more flexible in their location. No wonder both China and NASA are racing to secure key sites. The strategic importance of these discoveries is triggering what many call a new space race. In 2024, NASA Administrator Bill Nelson confirmed during a congressional hearing that the U.S. is in a race with China to secure water-rich areas around the lunar South Pole. He warned that China might attempt to claim these regions, drawing parallels to their actions in the South China Sea. This marks a shift in how NASA publicly discusses space policy. The concern is clear. The South Pole offers water ice, helium-3, and strategic positioning. Whoever establishes a presence first gains a massive advantage. China's plans are advancing rapidly. Their International Lunar Research Station, ILRS, aims for a permanent base near the lunar South Pole by 2035. The upcoming Chang'e 7 will explore shadowed craters for ice, while Chang'e 8 will test resource utilization technologies, laying the foundation for a long-term outpost. While NASA's Artemis program faces budget and schedule issues, China's lunar strategy is consistent and long-term. They're mapping resources, testing extraction, and preparing for industrial use. The first nation to create a sustainable lunar presence will gain influence over space travel, energy access, and potentially even security dynamics. Water ice can be converted into rocket fuel, drastically lowering the cost of space missions. Helium the 3rd of May one-day power fusion reactors. And the Moon's vantage point allows surveillance of space activity. As former Air Force Secretary Heather Wilson wrote, the first nation with a permanent lunar base will set the rules for space development, just as Britain's naval dominance once shaped maritime law. To appreciate the scale of this shift, we must acknowledge how limited Apollo's exploration really was. Between 1969 and 1972, 6 Apollo missions landed only on the Moon's near side, all within a narrow equatorial band. They missed the poles, the highlands, and the far side entirely. It's like exploring Earth only between Miami and Dallas. Apollo returned 842 pounds of samples, all from similar regions. By contrast, China's Chang'e missions have gone far beyond. Chang'e 4 was the first to land on the far side. Chang'e 5 returned samples from a young volcanic area. And Chang'e 6 just returned the first ever samples from the far side. These missions show that the near and far sides are vastly different. The near side has lava plains, maria, a thinner crust, and higher concentrations of radioactive elements, collectively called creep. The far side is rugged, heavily cratered, and has a thicker crust. It has almost no maria and far fewer radioactive elements. The South Pole Aitken Basin, where Chang'e 4 and 6 explored, is the largest and oldest impact crater on the Moon. It likely exposed deep mantle material, giving scientists a window into the Moon's, and possibly Earth's, interior. Differences in chemistry and isotopes between the near and far sides challenge our theories of lunar formation. China's discoveries are rewriting what we know. Gel-like substances, glass spheres, and mantle minerals reveal a complex, evolving lunar history. Water-bearing glass beads suggest water is widespread. Helium-3 provides a potential solution to the energy crisis. This isn't just about science. It's about the future of energy, space access, and global leadership. China's methodical, long-term approach is delivering results. With each Chang'e mission building on the last, they're not just exploring, they're preparing to stay. The moon is no longer a barren rock. It's a strategic platform, a treasure trove of resources, and possibly humanity's next home. The nation that leads in lunar exploration will shape the next chapter of space history, and China is currently ahead. Thanks for watching. Click the video on your screen for more deep dive content.